presented by Caltech.
Okay, thank you, Hiroshi. It's an honor to introduce the first speaker. Actually, before I do, a quick announcement. We had expected that Patrick Hayden would be one of the speakers on the program today, another former prize fellow. Patrick isn't here for a happy reason. Yesterday, he and his wife, Mary, welcomed a baby girl, Carolyn Eleanor Hayden. So we inaugurated not just the Burke Institute, but also Carolyn Hayden yesterday. And now in contrast to Carolyn Hayden, our first speaker, Guy Vidal, was not born yesterday. And actually I knew the name Guy Vidal before I knew the man. That story also involves a former prize fellow, Michael Nielsen. When he was here, he taught me about majorization, something in linear algebra I knew nothing about, and convinced me that it was important for understanding transformations among entangled states. And then Vidal, who was then a student at Barcelona, wrote a follow-up paper which extended these results. And I wouldn't have noticed an obscure paper by a graduate student at Barcelona probably, except that, why are you frowning? Except that my students read it and thought it was really interesting and explained it to me, and it was interesting. So I found out more about what this guy Vidal was doing. He was doing other interesting things, explaining the different ways in which 3 qubits could be entangled, stuff like that. So we invited him to visit, and after a few minutes talking to him, I thought, well, I'd really like this guy to be at Caltech, and this wish came true. He was the Sherman Fairchild Prize Fellow. He was here from 2002 to 2005, and while he was here, what he did really exceeded my wild expectations. When he was at Caltech, Guy initiated the study of tensor networks, with which he is now so closely and properly associated. This is a great topic because it connects together so many different things in theoretical physics. Guy's original motivation was to understand when a quantum computation is hard to simulate or easy to simulate, but the methods he developed are very powerful for simulating quantum matter, and now we're recognizing their relevance to things like the quantum geometry of space-time. Nobody explains this better than Guy, so here he is.
Thanks, John. Oh, perfect. Thanks, John. Is the microphone on? Okay. Thank you very much for this nice introduction. So I would also like to thank the Walter Burke Institute for Theoretical Physics for the honor to give one of the talks today, this symposium. Let's see. Indeed, I was a Sherman Fairchild Prize postdoctoral fellow at Caltech from 2003 to 2005. And what I want to tell you today these are ideas that I started thinking about back then. So what do I want to tell you about today? I want to remind you of the renormalization group. And I want to tell you a little bit about what tensor networks are. And then the worst part of the talk is when I try to combine tensor networks and renormalization. So this is one of the only equations I have for you today. Tensor network renormalization equal to renormalization group plus tensor networks. Some criticism we receive is that we spend half of our time drawing figures instead of doing calculations. And my only comment to that is that if you really try to draw the figures, you'll see that it's more than half of the time. But anyway, I'm not the only one drawing figures, and one of the main contributors to the work I'll describe today is Glenn Evenbley, who may be here or may not. Oh, he's okay, trying to embarrass Glenn. Hi, Glenn. So he was until recently also a prize fellow at Caltech, and now he recently moved to UC Irvine. All right, so what's the big problem we are trying to address here? we want to study emergent phenomena in quantum many-body systems. So you give me a bunch of electrons or atoms or whatever, and we want to understand how they organize them collectively, how they organize themselves collectively, to maybe give rise to a metal, insulator, maybe a superconductor, superfluid. You know, these days you can get lots of pictures from the net, so you just go on and talk about quantum many body systems. Ideally, though, the problem we have here is that we start from a microscopic description. We understand the interactions for these electrons or these atoms, but we would like to really be able to derive from these microscopic interactions how these systems behave collectively. And so let me try to define a bit more the problem we have. What we're given is this microscopic Hamiltonian, this local Hamiltonian for the many constituents. And what we would like to compute is the ground state or ground state properties. More generally, we would like to be able to understand the low energy collective excitations of this system. Or alternatively, in terms of what I'm going to call the Euclidean path integral, which is, in this case, just the trace of the exponential of the Hamiltonian, we would like to also understand this object because it can give us also this type of information. Okay? So examples are important. I remember last time I gave a talk at Caltech, I forgot to give an example. So quantumizing model. We're going to be talking about, as an example through the talk, I'll be talking about, or thinking about the quantumizing model, specifically a spin chain, one dimension, nearest neighbor interactions, some transverse magnetic field. And then in this case, the Euclidean path integral is going to be an object that lives, well, it will have the length. We're going to be talking about maybe a torus. We'll have the length of the spin chain and the inverse temperature in the other direction. And we would like to be able to recover well-known results, such as the phase diagram for the ISE model, where we have the magnetic field. As we change the magnetic field, we go from a symmetry breaking ordered phase with non-zero spontaneous magnetization to disordered phase through some phase transition. Okay, so that's an example that I'll be referring to during this talk. But I will also be switching, just to remind you that there is a two-classical partition function, two-classical ISE model, where now both directions are space, has a very similar behavior, and actually the partition function has a lot to do with the Euclidean path integral that I've defined before. Okay, so I'll be exchanging between 1D quantum systems and 2D classical partition functions. Great, and why do I talk about this example? Well, I'm not trying to be modest, that's the example that we understand. Other examples that we would like to understand is generically material science. The problem I was referring to, give me the basic constituents for a material and try to derive microscopic properties. Quantum chemistry, QCD, we really, we are naive enough that we want to solve QCD and we think that we should keep trying. And so what's the basic problem we have when we try to analyze these problems? It's the well-known exponential growth of Hilbert space dimension with the system size. We cannot use a computer. We cannot store this big wave function for the ground state efficiently. And so there have been many ideas, many proposals how to deal with such systems, and the one that I want to quickly refer to is the renormalization group. So in this case, we start by looking at our Hamiltonian, microscopic Hamiltonian, and we recognize that it consists of it has some couplings, J and lambda for the ISE model. So more generally, we could have many, many couplings. For the ISE model, we would say that all the other couplings are zero, only the first two are non-zero. And then the basic idea of the renormalization group is that we're going to study how these couplings change with the scale of observation. We're going to look at our system from farther and farther away, and we'll see that there is, in some sense, there is a way of defining an effective Hamiltonian. We'll obtain a flow in the space of couplings, in the space of Hamiltonians. And so this is the usual picture we have in mind. Here's just some section in 2 dimensions of this very large space of couplings. And what we identify there is that there is some non-trivial flow with some, so if we start with some Hamiltonian, as we change the scale, it will flow somewhere. Here we can see for instance, that we have, let's see, that this flow divides the space of Hamiltonian into two phases in the sense that if we start on the green region, it will flow to some fixed point. If we start from the blue region, the flow will take us to another fixed point. And we'll have these stable fixed points, one per phase. And in the middle, we'll have another fixed point, a critical fixed point, which will correspond to the phase transition between the two. So this is the old picture you've learned at, I don't know, primary school, or I'm not sure. So a very important ingredient in this conceptual framework of the renormalization group is the change of scale, right? We're talking about how the couplings of change as we change scale. So what do we mean by changing scale? And in this talk, we'll mean a constraining transformation. And of course, the people who propose the renormalization group also propose concrete ways of performing this constraining transformation. And so we have, for instance, Leo Kadanoff. I think there is an F missing here. What he proposed is the way to understand how to change the scale is by taking blocks of spins and replacing them with single spins. Okay? In this way, you effectively take blocks of spins into single spins, and then you zoom out, and you end up with a system that locally looks similar to the one you started from, but it corresponds to a different length scale. Excellent. So we have a rule. Maybe how do we replace 3 spins with 1? Well, his rule for one proposal was this majority vote. So you look at how many spins up you have 1, how many down you have 2. So you decide that there are more spins down here than up. So you replace the whole block with a spin down. Okay. Another way of doing this is Kenneth Wilson approach, where we look at the Euclidean path integral, and we recognize that it's an integral over modes at different energy scales or different momenta. And what we can do is to break this momenta into 2 pieces, one from a cutoff lambda into a new cutoff lambda prime. And we can make this integral just between lambda prime and lambda. And then when we make this integral, we obtain some effective description, some effective Hamiltonian here with new coupling constants k prime. And then we just rewrite the same Euclidean path integral in terms of this effective Hamiltonian with couplings k prime. Okay, and this leads to the exact renormalization group equation. And that is what generates, again, a flow in the space of Hamiltonians. Now, this is the story that we all know. Maybe some comments are that, well, the conceptual framework is fantastic. It helps us understand a number of things: stability of phases, universality, quantum criticality in general. And these proposals are also these concrete proposals are also very powerful. In particular, we can use this to compute the two-dimensional classical Ising model and get, say, critical exponents for it. And in this framework, we can use perturbation theory or also non-perturbative approaches to get a lot of insight. Now, what I would like to do in this talk is I want to steal all these ideas, all the ideas of the renormalization group flow, except that I would like to improve on the constraining transformation. And so what would I like to do? That's just a wish list. I would like a non-perturbative renormalization group approach. I would like to understand how to perform these constraining transformations. I would like it to be in a way that is universal, so it doesn't depend on the system. I don't want to go there and say, OK, I have 3 spins. I decide, because it's Tuesday, that I'm going to use majority vote to define this constraining transformation. I want a more objective and universal way of doing that, that it applies to a generic system. And yes, I want to solve QCD. So how far did we get with this? And by this, I mean over the last 10 years, there has been this effort in Tensor Networks to try to improve on renormalization group methods. And what did we get? Well, the first thing is we managed to reformulate the renormalization group using quantum information tools and concepts, quantum circuits, entanglement, etc. And when you reformulate something, you have to be careful. This is not just marketing. We're not trying to change variables to make it look nicer. We really try to get new insight. And so I would not be telling you about new ideas, how to deal with the renormalization group, if this this way of reformulating it in terms of quantum information concepts and tools was not fruitful. In the process, one thing that we learned is we came up with an efficient way of representing wave functions, and I'll talk more about this later on. So by trying to understand how to formulate the renormalization group, we ended up having a new efficient way of representing the ground state of a many-body system. But the good news is that we seem to, one of the outcomes of this effort is that we now have a universal non-perturbative real space RG approach. So I insist, it's real space, we work in real space, it's non-perturbative, we don't use perturbation theory, anything that looks like that. It does not depend on the strength of interactions, and it's universal in that we can apply it in principle to any system. So we are very excited about this, and I wanted to tell you a bit what the story is. But let me start with a slogan. The key ingredient on this development is the removal of short-range entanglement. And also, I'm sorry to say that, that we have not solved QCD yet. I'm sorry about that.
Quick question.
Yes?
Is there any restriction on whether or not your system is gapped or gapless?
No, we will be dealing with gap and gapless systems. All right, so the Tensor Network research program is much broader, and it has involved many, many people. And I couldn't list all of them here by far. We have maybe a community of 100 people or more. And it started more broadly trying to understand condensed matter problems. In particular, we were trying to develop new variational ansatz, new variational many-body wave functions to study frustrated magnets or interacting fermions or quantum critical systems. That was the beginning, but then it quickly degenerated into other much more interesting things. For instance, Xie Chen, who might be among us. Is Xie here? Okay, hi Xie. So together with her collaborators, they developed a classification of gap phases of matter based on the Tensor Network formalism. The Tensor Network formalism was not used there as a variational many-body wave function, but as the right formalism to issue a classification of gap phases of quantum matter. Nowadays, there are serious efforts to bring tensor networks or to use tensor networks in the context of material science, also in quantum chemistry, also in classical statistical mechanics. And the part that I want to talk about is the renormalization group. That's also one area that it has had an impact. And also I'll mention quantum gravity or holography. All right, so is there a clock somewhere? Okay, I'm assuming I have another 40 minutes. So it's very early, right? Okay, perfect. So let me introduce. Perfect, even better. Okay. So what do we want to do? Let me tell you about tensor networks. This is a broad colloquium or broad talk. I don't want to go into too much technical details, but there is a little bit I have to tell you. So what we're trying to do is we consider the wave function of n quantum spins, and we can always expand it into a product basis of the spins, spin up, down, up, down, up, down, and this gives us with some 2 to the n or exponentially many complex amplitudes here. And a tensor network, if I just had one drawing to describe it, would be this one. So what we're going to do is we're going to find a way of expressing these 2 to the n complex coefficients that describe the ground state in terms of something that looks like this, that I'm going to call a tensor network. And of course, what I need to do is first introduce this graphical notation that I'm using. And so if you see a circle, what you have to think is that this represents a complex number. If you see a circle with a leg, that represents a vector. So this leg represents an index. If you see a circle with 2 legs, that represents a matrix, and so on. If you see a circle with many legs, as you see here, that corresponds to a tensor with, say, n legs, n indices. Okay? So this explains this part of the equation. What we're doing is representing these exponentially many coefficients by means of a tensor with n indices. Excellent. So, and the other piece of notation I have to introduce, and you should be paying attention because there is a white spot here, and there will be a question for you in a minute. So, so the other thing I want to tell you is that if you see two tensors, right? These are two tensors, in this case, two matrices. This is a circle with two legs, so it's a matrix. Another circle with two legs, and that's another matrix. If they share an index, then there is implicitly a sum over that index. So in this case, if you see these two matrices with a sum over an intermediate index, what we are representing is actually is the product of two matrices which give rise to another matrix. Okay, so I hope this equation now is clear. We multiply two matrices to obtain another matrix. Similarly, here what we have is a complex number. There are no legs. And on the right-hand side, what we have is a vector, a matrix, a vector, right? That's a vector because it only has one leg. This is a matrix because it has two legs. So it makes sense. You can get a complex number by multiplying a vector times a matrix times a vector. Okay? So now, exam time. So I have this drawing for you, and I need you to tell me what that represents. Trace of what? Oh, okay, yeah. Sorry, that's Caltech, right? Excellent. So we seem to be following the idea. So why do we bother about this? Well, let me represent here a product of many tensors, and here the expression that I would have. This is already enough to represent the same information. It's just that if you give me this expression, the first thing I'll have to do is to draw this figure to try to understand which index is contracted with which. Okay? So now we are ready to go back. And here, so on this side, what we have is a tensor with many indices, n indices, representing 2 to the n complex coefficients. On the other side, we have a collection of tensors that are multiplied in some way. If we look at the number of open legs, there are n, as in here. Okay? So a tensor network is just a way of expressing this very complex object in terms of as a product of smaller objects. And again, why do we want to do this? Well, this wave function, if n is large, we won't be able to store it in a computer because the memory requirements grow exponentially with n, right? So maybe you can store in your computer 20 or 30 spins, or the wave function for 20 or 30 spins, but you cannot store 100 spins in your computer. And you will never be able to do that. So that's the left-hand side. What do we have on the right-hand side? Well, what we're going to do is we're going to use a tensor network. In this tensor network, there is this bond index multiplying two tensors, which will take some number of values, say chi. And the important part is that this chi does not depend on the number of sides, on the number of spins. So it's independent of n. Okay? So what we have on this side is each tensor has some number of coefficients. If it, in this case, for instance, this index takes 2 values and each of the bond indices chi values, this means that each tensor has 2 times chi squared coefficients. Okay? You have to specify 2 times chi squared coefficients to give me one of these tensors, and we have n of those. So the number of complex parameters that we need to specify here grows linearly in n. Okay? It's proportional to n because there are only n tensors, and the size of each tensor does not depend on the system size. So great, because it means that we can express, using only a number of parameters which grows linearly in the system size, we can express wave functions for arbitrarily large systems, well, for n qubits or n spins. And that's an efficient way of writing these wave functions. And you should be really upset about what I just said, in the sense that this cannot be an equality in general, right? Here we have exponentially many parameters. Here we only have order n number of parameters, which is linear in the system size. So what's happening is that we know that we are trying to represent states in a huge Hilbert space. This is the Hilbert space of n spins. This space is huge, has exponentially large dimension. And what we're going to do, though, is we're going to focus on just a small subset of these states, which are the ones that can be written in this way. Okay? So we are using a variational ansatz within the huge Hilbert space. We're just going to analyze some small part of it. But our hope is that this small part of it also corresponds or has non-trivial overlap with the ground states of local Hamiltonians. Okay? And this is motivated, this is a hope that we have, which is motivated by the observation that ground states of local Hamiltonians behave in a very particular way, and now I will have to talk about entanglement entropy and things that I decided to leave outside this talk so that I could make my point in the end. But this is the idea. We are trying to focus, to zoom in into just a submanifold within the Hilbert space, which we believe contains the states that we are interested in, which are ground states of local Hamiltonians. Great. So example of tensor network. Here's another example of a tensor network. That's the one I will be discussing a bit more today. It's called the multiscale entanglement renormalization ansatz. And I decided to use colors because I had a lot of time in my hands. And it's pretty. But what I want you to think when you see this is that this is indeed, again, an efficient representation of a many-body wave function. So look at these indices, the open indices down here. These are the open. There is one open index per spin in a spin chain. So you want to think of this as a variational wave function for the ground state of a spin chain, where the spins are in one-to-one correspondence to the open indices down here. Okay? And so you have all these tensors. They are connected in some way. We'll try to understand why. But the idea is this is another tensor network. And now the first observation I want to make is that in this variational ansatz for one-dimensional ground states, this variational ansatz extends both in space, so this direction here corresponds to the direction of the spins in the spin chain, and also in scale. Okay? I'm using a two-dimensional object to represent wave functions of in one space dimension. That's the first observation. There is a scale direction. That should sound like RG already. Now, why do we do this? Well, the idea is that then we can, as I told you, there are variational parameters in all these tensors. And what we're doing is we're trying to have variational parameters corresponding to different length scales in the system. Okay, so down here we have these variational parameters will relate to properties of very short scale, very short length scale. Whereas these variational parameters will modify the wave function, affecting a much larger region, so larger length scales. And the last thing I want to tell you about this tensor network, the meta, is that it's secretly both a quantum circuit and a renormalization group transformation. Okay? So I just introduced it as some variational wave function, but secretly it is also a quantum circuit and a renormalization group transformation, and I want to explain what I mean by this. So the first thing I want to think of this as a quantum circuit, as a result of a quantum computation. And what I need to do is, if you notice, there are two types of tensors here. Some tensors have 4 legs, 1, 2, 3, 4. I'm going to refer to those as disentanglers, and I'm going to think of them as gates acting on 2 quantum wires. Whereas there are other tensors that have just 3 legs, 1, 2, 3. So I'm going to talk about those as isometries. Okay? And what I want to do is I can always think of this again as a quantum weight, as a gate between 2 quantum wires, but where one of the wires is at a fixed state 0. Okay? So what I'm saying is that each of these tensors can be attached or related to a gate in a quantum circuit. And why would I do that? Well, first let me show you the next pretty drawing. So what I've done here is I've replaced each isometry explicitly with, I've added an extra leg and I've put a state 0. And so now what we can do is we can think of the meta as a quantum circuit where there is some time here. This is not physical time. This is not the time in the many-body system we're interested in, but it's auxiliary time in some quantum computation. And what we can think is that this meta is defining a quantum circuit U such that you start with a completely disentangled state of your n spins, and through all these gates going down in time, you introduce entanglement. You entangle these spins to end up with your ground state. Okay, so this is a quantum circuit representation. And the idea then is that from this perspective, what we're doing is that we're starting with a product state, and at different times, we introduce some amount of entanglement into the wave function. And this entanglement that we introduce at a given time or scale will be precisely at that scale. So by introducing entanglement at different times, we introduce entanglement at different length scales in the system. And that should make sense if we are trying to represent the ground state of a quantum critical system. We know that we should have entanglement or correlations at all length scales. So that's how the meta is introducing those correlations into the system. Great. So I told you Meta was secretly a quantum circuit. I also told you it was secretly an RG transformation. So let me explain what I mean by RG transformation. And what I need to do is I need to take a step back and go back to Kadanoff and his blocking proposal for Koszenian transformation. So here I have my lattice. These are spins. This is an effective lattice that I obtain from this one by taking every 2 spins into 1 effective spin. Okay? So this you can understand it as the blocking strategy of Kadanoff. But we're going to use some, well, in the meantime, we'll learn a number of things. And for instance, using Steve White with his density metrics renormalization group, what he proposed there, we can apply it here. What he's telling us is, let's not decide that we have a majority vote on the spins to decide what the next spin is going to be. Let's leave it to some variational energy minimization. So we'll ask we'll take the Hamiltonian, we'll constrain it by this transformation, so we'll obtain an effective Hamiltonian for the coarse-grained system, and we will ask, how should we choose this blocking transformation such that the effectively the energy in this projected Hamiltonian is as low as possible. Okay, so we have this universal way of proceeding where we just use energy minimization to understand how to take 2 spins into 1. Okay, so I want to take this as a coarse-grained transformation, and then I want to modify it a little bit to end up with the one attached to the Meta. And so what I've done here is, in addition to taking 2 spins into 1, these 2 spins into 1 by means of this isometry, I've added disentanglers before that. So instead of just taking, say, these 2 spins into 1, before I let this spin interact with the neighboring spin through a disentangler, a unitary transformation, and this spin interact with the neighboring one through a unitary transformation. And then, after that, I put them together into an effective spin. Okay, and so, I've been talking for now, how long?
You have 5 more minutes.
Great. So why are we? What's the point of introducing all these elements? Well, first let's look carefully at the blocking scheme. What we have there is that we have entanglement between neighboring sites. When these 2 sites are going to become the same site later on, there is no problem. This entanglement will be absorbed, will disappear, right? If you have two spins that are entangled, but these 2 spins are going to become the same one, this entanglement is gone in the coarse-grained description. However, if you have that, look at this. These 2 spins are going to be together in here. These 2 spins are going to end up together here. Now, if there is entanglement between these 2 spins, when you coarse-grain these 2 together and these 2 together, what you do is that you are propagating short-range entanglement into long-range entanglement. And you are promoting short-range entanglement into entanglement at a longer length scale. And that's not what you would like your renormalization group transformation to be doing for you. You would like a proper renormalization group transformation should take all types of short-range details and remove them from the system to keep only the universal features of the phase, which are a longer range. And so the solution with the Meta is this, that by putting extra tensors, disentanglers here, these are the ones that will disentangle these 2 spins before making the spin blocking, and that's the key of the approach, removal of short-range entanglement. Okay, so great, I have 5 minutes, so I will speed up a little bit. But the idea is that we have this Meta that defines an RG flow in the space of ground state wave functions. What do I mean by this? Well, this was a variational ansatz for the many-body wave function. Now, if I remove a layer of coarse-graining, then this gives me a new wave function, effective wave function at another length scale. And if I keep removing layers, I obtain wave functions at different length scales. So this is the basic idea here, that we have not just one wave function, but actually a collection of wave functions in a single tensor network, and this collection of wave functions describe a flow in the space of wave functions. So we wanted to have RG flow in the space of Hamiltonians, but we were not so lucky. We ended up in a RG flow in the space of wave functions. But actually, that's not so bad, because the Meta, as we said, it's defining a coarse-graining transformation. So now we can take a Hamiltonian and apply the same coarse-graining transformation and obtain the energy flow in the space of Hamiltonians that we wanted. Okay? And so there are some technicalities here. I'm running out of time, so I will skip them. But indeed, we can, if we have a local Hamiltonian, we can use this Gaussian transformation to obtain a new local Hamiltonian and therefore define an energy flow. Excellent. So let me summarize what we've seen so far, and then I'll really rush through the last part of the talk. So we have the meta. We've seen that it's a variational, well, that we have different variational parameters for different length scales in the system. It was secretly a quantum circuit, and then I had the sentence entanglement. So it introduces, this quantum circuit introduces entanglement at different length scales. Then, and also RC transformation, which removes short-range entanglement and preserves locality, and blah, blah, blah. So you know, everybody has, we are all crackpots, and we have this idea, and we tell everybody about it, but it only makes sense if this works. So let's see how this works in practice. So let's take these ansatz. Let's take the Hamiltonian for the critical Ising model, and let's perform energy minimization. And what we obtain, what we can extract from once we have optimized the ansatz, there are many details there, but this is the type of results we can obtain. So here what I'm plotting are the scaling dimensions of the primary fields of the Ising CFT. So we have the identity, the spin, or the energy density. These are the exact solutions, and these are the scaling dimensions that we obtain after optimizing the ansatz. And you can see that we're talking about accuracies of several digits, 5, 6, 7 digits of accuracy. We can also study disorder operator, so the non-local primary fields, fermions, and so on. And we see consistently that we are getting 6, 7 digits of accuracy. So something is right about the ansatz that can provide such information. And more generally, we can see the conformal towers. We can also extract the operator product expansion coefficients for the CFT, and so this is what we obtain for the Ising model, the exact solutions with corrections on the 4th digit. And more generally, we can extract the central charge, the scaling dimensions, the conformal spin, the operator product expansion coefficients, so we can extract all the conformal data just from the ansatz. Very well. How many negative minutes?
You still have 2 more minutes.
Oh, positive ones, that's, okay, so, yes? The system size?
Yes.
It's infinite. It's infinite. We can study infinite systems. Just exploiting translation invariance and scale invariance, you have a very complex representation where you just have to specify a unit cell of tensors and repeat it through space and through scale. So it was directly in the thermodynamic limit. All right, so meta and holography, quickly. More pretty drawings. If you take the same tensor network, you draw it like this. It starts looking like hyperbolic space more clearly. So there is the entanglement entropy. This ansatz was designed so that it would reproduce the logarithmic scaling of entanglement for critical systems in 1+1. And the calculation of how this happened is parallel to the area of minimal surface in Ryu Takayanagi calculation. On the other hand, we have also 2-point correlators decay exponentially with the distance, as a power law with the distance. And then that help us define some geodesic and so on. And so there was plenty of evidence that this had to do with holography, but it wasn't until Brian Swingle brought in the subject, he proposed that perhaps meta was a realization or could be used as a toy model to understand holography. And since then, a number of people have contributed to it, and I was really worried to learn that even John is thinking about these things. I'm sorry, John, for all the damage. But on the other hand, it's quite encouraging that maybe this indeed is a toy model to better understand quantum gravity at some level. Excellent. So I think that I'm going to cut it a bit short here. I wanted to tell you the new stuff, very recent, with Glenn Evenly from December and January. And the idea here is that we have been able to extend these ideas not just to spin change, but now we add the partition function. So the idea is that we can represent this Euclidean path integral as a tensor network. This is not an ansatz. This is an exact representation this time. That there is a well-understood standard way of writing Euclidean path integrals or partition functions as a tensor network. And the idea then, and so if the system is translation invariant, then we'll have just a single tensor that is repeated many places. So this is an exact representation. Again, this is not a variational approach. And what we've learned, and I'm going to really have to skip a lot here, is how to coarse-grain this. It took some time to prepare this, yes. How to coarse-grain this tensor network in such a way that we remove all short-range correlations in the system again. So, and the key again is using disentanglers. And so in this way, what we have is a flow in the space of tensors A that define this partition function as we coarse-grain it. And it's quite interesting when you apply this again to in this case, the two-dimensional classical Ising model. Now we have to get used to dealing with tensors and a flow in the space of tensors, so that might not be something you're used to, but this is what happens for the Ising model, classical Ising model in 2 dimensions. If we start below the critical temperature, we have some tensor that, as we coarse-grain it, flows into some very simple tensor, which represents the symmetry breaking phase, where the two possible magnetizations are represented. If we start at criticality, there is a flow that goes quickly into a fixed point tensor. This is only an approximate fixed point tensor, but you clearly see that the tensor is not changing. And above criticality, there is a flow of this initial tensor. You see, initially, all the tensors are very similar, but one is below critical temperature, the other one is at criticality, and the other one is above critical temperature. And what you can see is that even though they start being very similar, they flow to different fixed points. Okay, that's something you can see explicitly. And to our surprise, this tensor network normalization is actually also producing, as a side, a byproduct, a meta. So we were trying to run away from meta. We were trying to do something original and different, and we failed because we ended up just recovering, as a particular case, the meta. But this gives us a completely new perspective, which we are very excited about. So for the last 10 years, we were thinking about the meta as a variational ansatz. We give you a quantum circuit, and you optimize. So the quantum circuit is fixed, the wiring is fixed, but you have to use energy minimization to optimize all the parameters. Now what we are thinking is, well, no, actually here we have an exact representation of the ground state from the beginning. It's a tensor network representation, and we can use these coarse-graining transformations to produce a meta directly for the ground state. So in the first approach, we just have this variational class in the space of ground states, and we have to try to find the proper ground state. The energy is energy minimization takes thousands of iterations over scale. You have to go back and forth forever. You can get trapped in local minima. We don't know if in the end, the result is an optimized ansatz. You never know if it's representing the true ground state or not. In the new approach, we don't think of this as a variational ansatz anymore. We already have a representation, quasi-exact representation of the ground state, and what we're doing is we're transforming that representation into a meta. Okay? So it's much simpler. We don't need to iterate over 1,000 times over scale. Actually, we just need to run the algorithm once over scale. And we are just rewriting the tensor network for ground state. So we know that we got the true ground state. And we can certify how accurate that approximation is by just quantifying the truncation errors during coarse-graining. So it's a completely different perspective. All right, so it's time to summarize. I promised that I would reformulate or explain how to reformulate the renormalization group using ideas from quantum information, ideas and tools. And in the process, we found this efficient representation of ground states, the meta, which is now used as a toy model for holography. And we have this universal, meaning that you can apply it to any system, a non-perturbative real space RG approach, which actually ended up with 3 different flows, a flow in the space of tensors or ground states or Hamiltonians. There are relations between those. And the key ingredient in all these constructions is that we understood that what we had to do was remove short-range entanglement. Okay, that's the key idea. And now the truth, well, I show you results for 1+1 dimensional systems or 2-dimensional classical systems, and we are very happy with those results. But what about 2+1 dimensional systems, 3+1 dimensional systems? What about QCD? So we're excited about the recent developments that have strengthened the tools that we have for 1-dimensional systems, and we feel ready to continue to research that. All right, so a final remark. Entanglement renormalization. Oh, John, that's you. Entanglement renormalization and meta are things that that we started thinking about while I was a postdoc at Caltech. And interestingly, these new ideas of tensor network renormalization have been developed mostly by Glenn Evenbly, who is also a Sherman Fairchild Prize, or who was until recently Sherman Fairchild Prize postdoctoral fellow at Caltech. All right, thank you very much.